few minutes to get you up regarding a linear algebra problem 2.10. Okay. So basically, you are asked to show that, say for example, so you have an A matrix that is C m by n. Okay, not necessarily square. So I want to show that square root of m and the 2 norm is less than a infinite norm and less than or equals to square root of n and a2 norm. Okay, a2 norm. So this type of thing looks very tricky from the beginning. So you don't even know where to start. Okay, so I think first of all, it's too easy here. First of all, you need to understand that when we talk about this, we're talking about induced norm, first of all, okay? Induced norm. So for example, let's say we have a vector has, of course, this vector is, it doesn't matter, R or C. Let's put C like n by 1, okay? Is a vector. It's a vector. So therefore, I have a v sub I, which is C, okay, which is 1 by 1, okay, 1 by 1. So then I can write v is v1, v2, like v, let's say n, okay. So I have this one, and remember, writing this one is for convenience, but you don't forget about this because this is n by 1, okay? N by 1, okay? N by 1, not 1 by n, okay? So by convention, everything is n by 1. So what I'm trying to show you one thing is, what is the 2 norm? 2 norm is vi square, absolute value square, and you do square root. Isn't it? So what is infinite norm? So infinite norm is max of I, then vi, right? Actually, I'm doing individual vi, then is absolute value, right? So the reason we put absolute value is because of a complex, okay? Of course, you have learned what is v1 norm, right? So the v1 norm is just sigma vi and add all the I, okay? Make sense? Did I? So just to recall this. But you remember that among all this one, if I say that, so I know that, so can we say that vi is always less than for all I. This is obvious, right? This is obvious, right? So this is obvious. If you question me about this, then you are in trouble. Because I already pick up the maximum. So everything else is less than me, or there's that one guy equals to me. Okay, so in this case, I put this one in. It's obvious that 2 norm, you just everything together and have n of them, so it's n, those max, okay? Okay? And this one, square? No. This one, square. Okay? Then you square root. Okay? All right? So everybody is less than this. So then you have n of this. So it's a square root of n, what? V infinite norm, right? Okay? So with that, I can write, this is not equal anymore. This is not equal anymore. So it's less or than equal, okay? Less than equal. So this one is equal, okay? This is equal. Okay? Question?
sigma you sigma.
We don't sigma. Oh yeah, there's a sigma. Sorry. Oh, I already did the sigma. N is already sigma. This one.
Yes.
Oh, sorry. Yes, you are right. Okay, doesn't matter. So in other words, I can say that. Can I say that this infinite norm is greater than or equals to square root of n to norm? Is that right? Yeah, this guy greater than 1 over n, right? So are we closer? let's pull out this guy. Let's put this guy. We'll take a look. Okay. So let's talk about ax. We know that ax2 norm is less than or equals to what? Square root of n ax infinite norm. Okay. Because this is a vector, okay? This is also a vector. Okay? This is also a vector. Okay? So then this, of course, this is for all x, right? For all x. So what I'm trying to do here is just divide it by, let's do this. So I also know that my x2 norm is also less than or equals to x infinite norm, right? No, it's greater than. Okay, sorry. Yes. Is this true? Because the maximum guy is already here, and I add many others, and square root, of course, is bigger than this. So in other words, this is less than. Okay, so you inverse it. Okay, so this is true, this is true, this is also true. So we are closer, right? So this one divided by this one, and this one divided by this one. So what you are going to have is multiply this. So you have since you have A, B, C, D all greater than 0, so you have A greater than B and C greater than D. So then you have AC greater than BD. Isn't this right? So you just this one multiply this one multiply this. So you are going to get A2 norm less than A what? Infinite norm. And then you have 1 of square root of n here. Okay? So this one is shown, right? Okay? Okay? Yes? Okay. So that's the simple way you show those vectors, norms, induced norms. So it's difficult to directly show the matrix norm like this, but it's possible you discuss about induced norm. And of course I used x, yes, yeah. All these arguments. So, Derek? Yeah, so, but it doesn't matter. You guys can figure out, be careful, just be careful. M is not equal to n, you know. Yeah. Okay? So, I'm going to do more at 3:30. I'll be there, 3:30 p.m. SE 172. This is our lab time. Actually, it's 4:30. Sorry. I'll be here 4:30. I'll be here 4:30. Okay. So I'll stay for a week, and we can talk about lab. We can talk about assignments, and so have fun. We are having fun, right? So from now on, I wish you remember what is this RH infinity, okay? RH infinity space. Do you guys still remember what is RH space? I think it's a good idea we review all those spaces. Okay, that's excellent. So in the future, I probably will do a little bit about homework questions and discussions before the lecture, just for like 10 minutes each, okay? So in here, I want you to look at the definition here. Okay, it's here. So it's called all proper, real, rational, stable transfer function matrices. So I wish to say transfer function matrices. Okay, transfer function should be have function. So small Gij(s), okay, Gij(s), Gij(s), then you put this one as a matrix, and Gij itself can be written as numerator Ij divided by denominator Ij, and this one is kind of Ij element of this one. So when we see what is proper, rational, okay, rational means what? It's two polynomials, okay? So these are polynomials, okay, polynomials, okay? Otherwise, irrational, like e to the power of s, e to the power of minus s. So this is irrational, okay, transfer function. Of course, square root of s is also not, so that's a fractional order stuff. Proper is saying that it's rational, then proper means the relative degree issue. So improper, that relative degree should be, this relative degree should be degree of this one greater than this one, not even equal. So if it is equal, it's still proper, but it's not strictly proper, okay? So in fact, sometimes you will see, oh, strictly proper and real, rational, stable matrices, okay? So that's each component. But how we can say stable, we need to do a Macmillan form, okay? Macmillan form to decide what's this. Okay. So let's see several examples here. H infinity functions. So they are H2 functions, H infinite functions. So this is a rational proper, and this e to the power minus s. This is a delay. Because of the delay is magnitude always bounded. So the magnitude of delay is always 1. Okay. So e to the power of j omega is magnitude is 1. So it's not going to cause a big issue here. And I still believe that we should not include this. This is irrational. So, but somehow they believe this is still rational. Oh, I'm sorry. So it's not RH. Sorry, it's H infinity. Okay, H infinity. It's not RH infinity. Okay, it's not RH infinity. So there is also a concept regarding anti-stable when you have all proper, real, rational, anti-stable transforms. So RH versus RH minus. So I told you last time, whenever you want to have anti-stable transfer function, then you just replace S with minus S. Okay. H infinite norm. It's a worst-case norm I mentioned multiple times. And it's like an induced norm of a matrix. So, of course, this is no longer a simple matrix. It is a matrix that is frequency dependent. So therefore, it's frequency dependent. You still need to talk about maximum over omega. So this is the peak over all omega. And so that's a review. Last time we started with internal stability. Okay, so we have heard about well-posed control systems. You must not have pole zero cancellation. That pole zero pole is unstable. So you should not have a non-minimum phase zero, and you should not have a non-minimum phase zero cancel out with unstable pole. So in this case, I want to remind you a few things. So we say pole, the real part of this pole is living in left half plane. So left half plane, okay? So it's also called stable. But if it's greater than zero, it's called right half plane. It's unstable, okay? Stable. And for the zero, so it's the same thing. You have zero in here, okay? So it's less than zero, so it's a left half plane zero, okay? And if this is greater than zero, then this is a right half plane zero, okay? Right half plane zero. There's no such thing called unstable zero. Whoever used this term is not a real control expert. Because zero will not affect your stability at all, right? So there are no such thing. So you should not say unstable pole. You can say unstable pole, but you cannot say unstable zero. Don't use that term for my class, please. I know some people use unstable zeros. Don't use that, okay? You rather say RHP zero. Or really you can say non-minimum phase zero, okay? Okay, this non-minimum phase NMP, non-minimum phase thing, is something very difficult for a control. Okay, because it will induce it's like step response. Usually, you give a command, say go and follow me, then it will follow you. Okay. But if you have a non-minimum phase zero, the zero is on the right half plane. You say, follow me, they will go directly this way. They don't follow you first. The direction is wrong. Then after that, it will start to come back. So this is called non-minimum phase behavior. This thing is called non-minimum phase behavior. Okay, it is anti-intuitive. Okay, it is especially when you have human in the loop. People do not have this training. Okay, and then human will thought, oh, I should do this. Then you will make the things worse and worse and crash. A lot of accidents in industry is linked to this. It's linked to this non-minimum phase behavior. Okay, non-minimum phase behavior. So in the next chapter 6, we are going to talk about performance limitations. We are going to have a further appreciation of the non-minimum phase theory. But in here, internal stability, to formalize it, is using a simple, what we call the GAN of 4. The GAN of 4. Okay, GAN of 4. The reason we talk about GAN of 4 is sometimes if you look at different combinations, you have 4 different combinations. Then you look at this is stable, stable, stable. There is a one not stable. So you have to make all of them stable. Okay? All of them stable. So that's intuitively true. But how we can say that check it in a simple way. Again, we return back to the pose-zero cancellation in the right half plane. Okay, the right half plane. Okay, so here we clearly have 1 here. Okay, I have 1 here. Okay. So for P is siso, K is siso, life is easier, right? But what if my P is a matrix, say like 3 by 3, K is also 3 by 3? In this case, it's really difficult to check, isn't it? Very difficult. So the first thing to check is to see whether everything is well posed. So well posed is a much weaker condition. Well posed is a much weaker condition. Okay, much weaker condition. And I want you to know that the K infinity and P infinity. So the meaning of K infinity and P infinity is not very clear to many of you. Okay, let me give you some more insights into K infinity. So let me show you that if you have K or P, you also can write NK divided by dk, right? Dk. You can say pk dk. You say that, oh, sorry, P. No. It's NP and versus dp. So numerator polynomial. So this is a siso setting, right? But in the MIMO, you cannot write this way, can you? You cannot. So then we need something in the MIMO setting, right, in a similar way. So we should do NK and DK. Okay, something like that. Or you can also write in DK. Okay, you can write DK inverse NK. Okay, depending on left or right inverse. So it's always possible. But for the siso case, this is the same, right? The siso case, this thing and this thing is the same. But in the matrix form, it's different. So therefore, we need to be careful about factorial. So this is a matrix, this is also a matrix. Okay? So we need to think about this carefully. So that's why we need to talk about factorial, factorization. So it's called factorization. So we're going to do it. So Coprime factorization. Coprime. Yeah, of course we need to talk about coprime because otherwise it's coprime. Otherwise it's meaningless. You have a lot of things you can just cancel out. So it has to be. So we're going to talk about this in the next. But first I want to tell you that in the siso setting, come back in the siso setting. So when we see K infinity and P infinity, okay, so usually in practice these are all rational and proper. In other words, in our say for example, I have 1 plus s plus 2. So this is K infinity. So the K infinity, this one will go to 0, right? So if you have other things, the relative degree greater than 1, greater than or equal to 1, then its transfer function g omega L will be 0. Because the degree here is higher than here, right? So the infinity will go, so everything is, so in other words, they will be all 0. They will be all 0 in practical systems when everything is proper. But it's strictly proper, okay? So this will be 0. But sometimes it's not strict proper. This one maybe is 1.5. It could be. Say for example, s plus 1, s plus 2 plus 1. So then infinity will give you what? 0.5, right? Okay? 0.5. So it's possible. It's possible. So then it's possible that this one happened to be 1, then 1 minus k, so k minus 1. Let's say this is minus 1. So then you have 1 plus p infinity, k infinity is 0. So it's not invertible anymore. Okay? So you got singularity there. There's no reaction whenever you do. So in other words, having the well-posedness makes sense. Otherwise, you input something, that thing at omega is infinity is 0. So you have nothing out. So no matter how you do it. So it's something we don't want to talk about. It's not well-posed. So remember, well-posed, if everything is RH infinity, I think almost is guaranteed. So in other words, it's like x is ax plus bu, y is cx plus du. Okay. In other words, okay. In other words, this thing is linked to the d, okay, the d term, the infinity. Yeah, the infinity, k infinity, and p infinity. Okay. So if you have a realization like xk, ak, xk, bk, uk, so it's a realization, okay? So you don't want to do, so these are the variables linked to the k realization, so it's a realization. So we don't want to write this messy form. I simply say this is ak, bk, and ck, dk, okay? Okay, ck, dk. So it's a state space realization. When we say this is 0, that means this is 0. Okay? That means it's strictly proper. Okay? Say, for example, if we have s plus 1 versus s plus 2s plus 1 and s plus 1. Okay? In this case, its realization dk will be 0. Okay? But in this case, this dk will give you 1, give you 2. Okay? When s goes to infinity. So in other words, this is 2. So in summary, that's why we need to talk about RH family. This is a big family of infinite members, about all the real, proper, stable transfer functions. All of them. Okay? So we limit our discussion on this. Okay? On this. So in this case, then we don't need to worry about the well-posedness too much. Okay? And if the D, if it is strictly the proper, then it's automatically well-posed. Okay? Well, we have seen this example. So you have P, you have K, both are 2 by 2 matrices. Okay, then PK will be like that. Okay, P times K. So there are some cancellations. In the first one, there is a cancellation here. Okay, so then we know that 1I plus PK, you want to inverse. So this one must be non-singular for any variable, non-singular. So in this case, it is okay to have an inverse. This guy add 1. So you have a s plus 2. Here you have s plus 2. Then you inverse. That's why you have s plus 2 in here. And then this term is a little bit more complicated. So then this inversion, okay, well, existence or not is very important, because those sensitivity functions are linked to the, this is just like a loop transfer function. 1 plus L is a loop transfer function. Okay, so you can see there is one unstable mode in here. So the whole thing is not stable. Okay, because you have a transfer function. If you put pk in here, so you have a closed loop transfer function, right? Okay. So you think about in the cycle is a this is a one is a pk over 1 plus pk is your closed loop transfer function. So then 1 over 1 plus pk. In MIMO case, you have to talk about this. Okay, matrix inverse. In other words, we need to check about this guy's determinant, but that's not enough. And the determinant looks fine. Okay, looks fine. Okay, looks fine. So checking this is not enough. Checking this is enough. Okay. So having this determinant, no zeros in the closed right half plane, does not necessarily mean this thing is stable. Okay, which is very true. Okay, which is very true. Okay, so we need to return to this question. You need to pay a little bit of attention about this thing. Okay, when is MIMO, you can write in this numerator denominator case in the matrix form. You have to write this thing. So next we are going to talk about Coprime factorization over the RH infinity. Means it is all it's all stable, proper, real transfer function matrices. Okay, matrices. Okay, so this is a matrix. Okay, so two polynomials. So we're talking about two polynomials. Okay, coprime, if they have common factors, only common factors are just constant. So that constant is just the scaling, okay? But you cannot have a factor like 1 plus s, 2s plus 1. You cannot have those common factors, okay? You don't have those common factors. Then we call it coprime. So you don't have any common factors, so it's called coprime. So this is easy to understand, okay? But giving a polynomial, how do I know these two polynomials are coprime without doing factorization of everybody? Okay, so especially when you have a high order polynomial, like a 10th order, okay, you have another 10th order. Do you know whether they have a common factor? You need a way to check it. Okay, that's non-trivial. It's not easy, but there is a guy called Bézout. He invented a method. Okay, by transforming one method to another one. It turns out Bézout, identity, okay? Is there his name somewhere? Yeah. Bézout. I think it's French name. Bézout identity, okay? But his name is not mentioned in the slide. So this is called Bézout identity. Okay, Bézout identity. So don't ask why, and it's in the literature to prove that. Okay, if you have, let me do this. So, okay, that's too much. Okay, let's do this. So you have two transfer functions, M, S, N, S in RH. So right now we are not talking just a very simple polynomial anymore. We are talking about transfer functions. So it's a polynomial divided by polynomial, okay? So in RH infinity, if these two transfer functions are considered as a prime, if and only if the common factors are stable. If they can have common factors, okay? Remember, if these two, the first bullet point, if you have two polynomials, they say these two polynomials are coprime, then they cannot have common factors. But let's assume that M and S now, they are no longer just a polynomial, it's just a ratio of two polynomials. So these are two transfer functions. M has numerator and denominator, N has numerator and denominator. Then we say whether these two transfer functions are coprime or not. It turns out that the definition is they are coprime if and only the only common factors are stable the invertible transfer functions units. So in other words, so if you have common factors, they are stable. The common factors are stable, it's fine. Okay? Or you don't have. Okay, if you don't have. So stable and invertible. So in other words, H and H infinity can be RH infinity as well. Okay? So in other words, this H maximum can be relative degree 0 because this guy is a relative 0, okay? This guy is relative 0. So the inverse is also relative 0, right? So this is RH infinity and the inverse is also RH infinity. But not this one. Not this one. If this guy is RH infinity, but its inverse is not. Okay? So it's something different, okay? Different. So that's why lead-lag compensation makes some sense. So it's relative degree 0. Okay. Well, so we assume we find an H, which is the inverse is also RH. So then only common factor are stable and invertible transfer functions. Okay, so H, MH inverse, NH inverse, they are all stable rational functions. Okay, so that's what they say. So on the other hand, that they say, to check whether M and N, I'm talking about transfer functions, M and N are coprime or not. If you can find two stable RH transfer functions, again, a polynomial is not RH, okay? RH infinity. Say for example, S squared plus 2S plus 2. So is this RH? Yes, RH infinity. No problem. Is this RH? No problem. Okay? Is this minus S also? No problem. Okay? So now I'm saying you only have this guy. Is this RH infinity? No. Okay? No. It is not. Okay? Because the relative degree is 0 minus 2. It's minus 2. So relative degree greater than or equals to 0. That's called rational. Proper. Okay, sorry. Proper. Okay. So relative degree is definition. Relative degree is the degree of denominator minus degree of numerator. Okay? So in this case, this relative degree is 1 minus 0, this is 1 minus 1. Okay? Okay, so. Okay, so let's go slowly. And so I gave you two transfer functions. Can you check they are coprime or not? So Bezout identity. This is called Bezout identity. Okay. So Bezout identity says that if you find me two other transfer functions, that is RH infinity. Okay. Then you multiply this or make it 1. Make it 1. So that's exactly the case. So this is for scalar transfer function. So these are a scalar case, okay? Sizeable case. Sizeable case. But for the MIMO case, things are a little bit different. But you need to distinguish between left or right. Left coprime or right coprime. Okay? So left coprime is basically saying that we usually use tilt as left coprime. Use the original one is called right coprime. Okay. Remember the tilt here is to say left coprime factors. Okay, so you have two transfer function matrices M and N. So you have a matrix, you have another matrix. Are they coprime? That you need to talk about what do you mean, left or right, okay? So, so like here, okay? You can write this manner or this manner. They could be different. Could be different, okay? So left or right coprime factorization, okay? And it's allowed to have common factors, but those common factors must be stable and invertible, okay? So we have a subscript R means left, okay? Oh, sorry, right. So basically, you have something very similar to this guy. It's also Bezu identity in MIMO case, matrix case. And so this is already well-established, just definition, okay? And you have M and N, so you have XL, YL, so you have M and N, so left coprime factorization. So you have this format, okay, this format. Then you write this way, so you exist to this, So the question is, we know that I have a transfer function. We write numerator, denominator, right? Denominator. Okay. So I want to have a MIMO system, okay, MIMO system, to be written also similarly like numerator and denominator. That is called coprime factorization of MIMO system. Okay, MIMO system. There are systematic ways to do this job. Okay, do this job. So usually we go back to the state space. Say for example, I have P, the plant, state space realization ABCD is P. And in the linear system, we have learned that we assume this is both detectable and stabilizable. Okay, and F and L is A plus BF is a state feedback. This is observer. Okay, observer, and these are both stable. Okay, pick up F and L. It's not unique. Okay, F can be anything, L can be anything, but you only need to make this one stable. Okay, state feedback is stable and observer dynamics is stable. So in this case, very interestingly, so you want to have M is a transfer function. You stack with YL. You put N. So this is a right coprime factor, a left coprime factorization. Let me go back a slide. I'm kind of not sure. It's very interesting. So this is a little bit unusual. Okay. So usually when we have a right coprime factorization, then from Bezu equality identity, we should be able to find X and Y R. But now they use L. Okay. They use L, and they said this one and this left and right coprime factorization are linked by this and this. So okay, so this is a MIMO transfer function matrix. So this is a transfer function matrix. This is also transfer function matrix. So it's stacked together is transfer function matrix. So you write this one, then can have a realization of like this. Okay, and here this is the right. This is the left coprime factorization, and the Bezu equality identities XR is from R. So R and L looks like swapped, like that. Okay, and overall, you have a realization like this. Okay, the derivation of this one in the textbook, and people studied this one extensively in the past. And from left and right coprime factorization, and then you have this identity. Okay. And again, so this is a right coprime factorization, and these are from left coprime factorization Bezu identity. So it's very tangled. This one is identity. Okay. So in the end, say for example, this is a 2 by 2 transfer function matrix. You also have a 2 by 2, 2 by 2, 2 by 2, 2 by 2. But you have two different forms. Okay? And each of them, you stack them so you get 4 by 4, right? 4 by 4. Okay? So, so-called right coprime factorization, left. So think about this is a generalization of a transfer function of size of cases, numerator and denominator. So the reason they do this is to make many cases discussion much more intuitive. Okay? So when you supposedly you find a way to write the transfer function matrix also in the matrix coprime factorization format, then how we can check stability of the system. Okay? So it's something like this. So if you have a coprime factorizing, this is right, this is left, okay? So following conditions are all equivalent. So feedback system is internally stable. So then you can only check, this is a transfer function here. You have a, okay, so let's do this. So you have P is N and M, K is your controller. You got controllers, coprime factorization is right, this is left. Okay, so with tilt is usually is left, without tilt is right coprime factorization. So if you can find a way, let's assume that you can do this. Okay, let's assume that you can do this. There is a step summarized in our textbook. Follow this step, you will be able to get this. In the homework, you have a way to practice. Okay. So then, with these coprime factorization factors, how we can check internal stability? So it's N, M, and U, V. So you use all the right coprime factors. Okay, you can do that. So if you feel this is trivial, if in size of case, yes, it is trivial. It is trivial. Okay. It is trivial. So if this internally, so then this is called invertible in RS infinity. Then it's called internal stable. Again, if the system is internally stable or not, I give you a transfer function matrix. It is difficult for you to do. If you have two transfer function matrices, P and K, they are MIMO. Tell me, when they hook up in a closed loop thing, whether this is well-posed, internally stable? No, you cannot check it very easily. Okay, you cannot. But using coprime factorization, it becomes possible. Okay, and same thing for left factors, coprime factors. This is right coprime factors. So it turns something like that. Or in other words, we talk about this is smaller matrix, MB and U minus is invertible. And this is invertible. So I believe this is trivial. This is a trivial. It's still based on the original definition in here. Again, we are talking about transfer function matrix. Okay, KSPS is a transfer function matrix, and each one has IJ term. Okay. So when you do this type of thing, you derive, you end up in here. So you can diagonalize it. You can have this. So that's why you can say you should make this one invertible, this one invertible. Okay. So I hope you understand why we need to even talk about it. Because in the MIMO case, you have a generalized numerator and denominator situation here. And it is called coprime factors. And you have left and right. So let's see an example. So this is a SISO case, okay? This is a SISO case. Single input, single output, okay? So we make this one, we assume we have a common factors like s plus 1. So what I do is n, this is n and m, okay? It's n and m, so n divided by m, okay? Or n, m minus, okay? Inverse. So you can see this one n is taking a numerator divided by this. You cannot use a denominator, a numerator, right? Numerator is not RH infinity. You cannot use a polynomial. This polynomial is not RH. So to make it RH infinity, so you assume that you have a factor, you find out alpha. So make n and m, okay? This one will form a Coprime factorization, okay? Factorization, okay? So you can see n and m, all the relative degrees is 1. So this is also relative degree of 1. So, but how I can find out x and y? I want to find my x and y. So, but we know x and y will satisfy this Bezier identity. So you have a stabilizing controller for P. This is a stabilizing controller here. And you also do the u divided by v, so this is factorization. Of course, it's a size, so it's very easy. But you cannot use this is u, this is v. It's not RH infinity. So what I do is I choose the u itself is this one, and v is 1. So it's funny, right? So u is this guy, and v is this guy. V is 1. Okay, v is 1. So in this case, u and v. So I use this divided by 1 is still my k. So write this k is u divided by v. V is 1. So this is also a Coprime factorization. So we didn't say the orders, or there's no restriction. So I put this uv here. I also this is my checking. So I check mv and nu is something like this. Okay. So we choose xs and ys, the beta like this, So everything looks good. Everything looks good. So then. So this is a way to find out this beta s. So then everything is stable. Okay, everything is stable. This is just a different way of looking at the numerator and the denominator. In the MIMO case, you should not simply use a polynomial. You need to use a RH function. RH infinity function. This is RH infinity. Okay. So good news is in my lab, life is much easier, and you can find out given A, given B, given C. So you always can find out F and L. Remember why we need F and L? F and L is because we can use a steady space formulation to find out this F and L, because ABCD is already known. Giving a P transfer function matrix, there is steady space realization. So find the F and L. It's not necessary to be unique, okay? To be unique. So then you will be able to write this format. So then you do transfer functions of this, given A, B, C, D, you have transfer function. Then you do a partition, you will get your M and N, and X, L. So let me just mention this one to you, that whenever you do this one, you put A, B, then when you want to do the feedback here, then you have no idea, you put just I means identity matrix. Okay? Identity matrix. But you need to find, so this is F, okay? Or you do the pole placement. So if you desired poles then you put here, then you can get F. That's one way. Another way is, if you have no idea, you just put identity in here, and you get this. Or you know what is the pole of your observation dynamics, observer dynamics. So giving the pole positions, you can solve what is your L. Okay, what is your L? Again, I assume you know the LQR in linear systems. Okay, linear systems. So let me just say something about LQR. Because this is a constant reminder, I assume you know this. But what if you do not? You don't remember clearly? Let's do this. So let's assume that I have system is AX plus BU. Of course, this is a MIMO because Y equals X. Okay? Y equals X. This is state feedback. State feedback. So I want to design a controller which is minus K times what? Times X. Okay? Times X. So this is called state feedback. So, but I want to decide the K. How to decide what's the best choice? We don't know. So you tell me. So here is something called LQR. So I have a matrix Q that can penalize my X transpose X. So this is a quadratic. Okay. Q is semi-positive definite. So this is a scalar. It's a cost. This is a scalar. Okay. So it's this one and this one. So it's a scalar, okay? And I have another scalar that this is a positive definite, okay? And you have U transpose U. So this is a MIMO, okay? All MIMO case, vectors. So because all these are function of t, right? So function t, okay? Then I do d dt, and I add all these things together and integrate this from 0 to infinity. This is my j. Of course, j is a function of k, okay? J is a function of u, depending on how you choose the u, actually. So initially, we assume the u is ux, actually. So this is a control law. We don't know this is exactly the linear law yet, okay? So it turns out that it's beautiful, and that we can solve. So this is the problem formulation of LQR, okay, LQR. So then if let's use F in here. So because if I put this one in, then doesn't matter. I remove this negative sign; it can be absorbed inside. So then my closed loop system is A plus F plus BF X. Okay. So then I know that the xt will be initial point, initial condition, and you have E minus A plus BF T, right? So that's a decay. I should be accurate. So x0 should be here. So this is a matrix, this is a vector, okay? So this is a vector. I cannot put a vector in front, okay? So in the MIMO case, be careful. Okay? So then then you need to choose the f such that this x will decay as desired, so that to make this thing minimum, okay, minimum, okay, make this one minimum. And it turns out that the solution for this minimum will happen to be u is f is a fx. Okay, there's a pretty lengthy derivation from calculus of variation. So we're not going to talk about this LQR questions, and so you need to solve algebraic Riccati equation to get this. So this actually is called, is linked to the R inverse. Is this supposed to be P divided M input, N output, N. So this is a matrix. So this is F is B, and I think it's B. B is M by N. So this is M by N. This is B. B should be here. I remember B is here. And yeah, so something like this. Then you have another one is so M by N, which is P. It's M by M, M by N. So this is M by N. I think we'll have another one called P matrix. So this P needs to be solved by something like PA plus AP is Q. Okay. So then you solve this P. So you get this. So you can see design tuning knobs are here, because you choose different R, Q, different R is a weighting matrices, then they will show up in here. Okay, they show up in here. So then you get different P, so you get F, you get this, different F, it shows in here, so you decay differently. So that's the solution. It's called LQR control. So this LQR behind this one. So I think this is a Q, this is, this is a Q, this is R. This is Q, this is R. Okay, this is R, the weighting. Okay, so you have no idea, you just put I, identity matrix. Okay. I think we spent quite a good time today. Our main focus was on Coprime factorization. Okay, I think it's a good idea. We should take a look of this LQR. We only talk about state space, talking about this. I remember now. I sent the author, Keminzo, I sent him an email. In 2002 or 2003. I sent him an email. I complained to him, saying that this textbook is so hard to read because he's using LQR without covering in chapter 2. So he should add chapter 2 LQR, chapter 3 LQR contents in there. He didn't do it. He didn't do LQR. I'm pretty sure he didn't do LQR in chapter 3. He didn't do. But he used the LQR stuff in here in chapter 5, internal stability. How to choose, how to do that. So that's That's the problem of this book, okay, of this book. But actually he covered Riccati equation in chapter 12, okay, and chapter 13, okay, chapter 13. He should have put chapter 13 some of the stuff in here. So let's take a look. Chapter 13, he presented it in a different way. Okay, I'll give up. LQR is quite important block in linear systems. Okay, I think it's better idea I give you a self-containing module. You take a look of LQR section. What is LQR? I already give you a flavor. LQR is an optimal control solution. Okay, giving A, B, you don't have C, you don't have a D. Then you have performance index. You penalize your trajectory of your X. You penalize your control energy. Okay, penalize control energy. Then you try to find the best control to make it happen. So it turns out that the best control is a linear control. But initially we don't know. So initially we should understand we use state feedback or have a control law. Okay? So, and there's some lengthy derivation about this calculus of variation. Well, we can use Lagrangian type of discussion, but that's another at least 1 or 2 hours lecture on that. So I'll pick up this part. By first giving you LQR self-containing reading. Okay, just read that part, maybe less than 10 pages. Pick up this one, so you know what exactly happened behind the LQR command we used in here. LQR command we used in here. But otherwise, this is just this one. Okay. Because although it's very simple to simply type in LQR, you really need what's behind. What's behind is the formulation like that, the calculus of variation, the state equation, co-state equation, and algebraic equation, algebraic Riccati equation, and the Lyapunov equation, and so on, so forth. So all these are condensed. You should pay attention to understand what's behind LQR. Okay. Although we have LQRs presented in the book, but it's in a very different H2 type of formulation. Okay, it's quite different. Okay, 253. Okay, let me double check. Yeah, it's different. It's different. Okay. So far I know that I'm trying to make this course a practically useful course, but it is of course very demanding on mathematics. Okay, on mathematics, and it is highly rely on how good your knowledge is regarding linear systems. So in chapter 3, there's a linear systems. Okay, usually in the linear systems, we should contain LQR optimal control, but he didn't put in, so that's disappointing. And so I'm going to send you that 10 pages long reading for LQR. All right. Or I give you a PDF, say read from this page to that page. Then if you have trouble, you can extend your reading. Okay. Make sense? So we're going to meet again at 4:30 today in SC1 172. If you are registered, you must attend. If you are not registered, you don't have to. Okay, so it's optional. Well, I'll let you go for the rest of the day.